Welcome to the fifth and hopefully final video in our Class 24 series of lecture videos. Hopefully we will go fast through this. Alkynes. It says briefly, but we'll see if I can stretch this beyond 10 minutes. Hopefully it doesn't put you to sleep. Alkynes are easy, right? They're just like alkenes that you have across the same carbon, just perpendicular to each other, and two of them, 2 pi bonds, perpendicular. There's ethyne, which we also refer to as acetylene. Here's 3 hexyne. Don't be fooled. There are 6 carbons in this. 1, 2, 3, 4, 5, 6. Yes, sp hybridized carbons are linear, and we tend to lose track of them, right? Because we're used to counting carbons at vertices, right? Like angled junctions. But some catalogs and textbooks actually have angled junctions at the sp hybridized carbon, right? Just to remind you that there is a carbon there. Recall the pKa trend. Alkynes are the most acidic with a pKa of 25. Wow, almost almost 20 orders of magnitude more acidic than alkenes, sp2 hybridized carbon, which are about 6 orders of magnitude more acidic than alkanes, right? pKa of 50, sp3 hybridized carbons. And this, of course, the pKa is all referred to pKa in water as the solvent. Synthesis of alkynes, well, double elimination, double E2 of a dihaloalkane. How do you make a dihaloalkane? Well, that would just be adding Br2 molecular bromine to an alkene, right? Remember that? And then what do we add? Looks like sodium amide, 2 or 3 equivalents in liquid ammonia, followed by water, and we get an alkyne, 1-butyne in this case. What do I mean by double E2 elimination? We're trying to go fast. I don't know if we can make it. Oh, look at this, it's messy. Here we go. Here's 1-butene. We've added Br2. We get our dibromide, right? Remember the mechanism for this? Here we do a double E2 elimination. Our amide comes in. Oh, our amide's missing an electron. There we go. And we pluck off proton from this beta carbon, carbon 3, create a double bond between 3 and 4, kick out that bromine. Now we have an alkene. We have another NH2 come along, right? Sodium amide. It plucks off this hydrogen from carbon 4. This is our second E2 elimination, and we get butyne. And here is where I have, shown you that there are 4 carbons explicitly by putting a kink in that sp linear carbon, right? Oh well. All right, there you go. Double E2 elimination. Let's go get through this video before we put anybody to sleep. Where are we? Oh, we're tipping the camera. Here we are, reduction. We can reduce alkynes selectively. Isn't that neat? Say you have 3 heptyne, we could use H2 gas and something called Lindlar catalyst to stop at an alkene. Isn't that cool? In which case we added the hydrogens to the same face of the alkene. We get this very specific cis geometry, which is the less stable thermodynamically geometry for alkenes, right? Because there's more steric hindrance than you would have in a trans alkene. What is Lindlar catalyst? It is like palladium on carbon poisoned with lead acetate and something called quinoline. That keeps your alkene from adsorbing onto the surface and getting reduced. Because remember, an alkene in just palladium and carbon with hydrogen gas present would be reduced. How do we get the trans alkene? Well, we do something called a dissolving sodium metal reduction. Doesn't that sound fun and dangerous? It is. Here we go. We have liquid ammonia. We throw in sodium. We get another very intelligent form of the color blue, which is basically like free electrons roaming around in liquid ammonia. And they do something interesting to this alkyne. They reduce it. You gain electrons. You get a nice trans alkenyl anion, which you quench with water later. And there you get trans 3 heptene. Let me show you the mechanism. I remember getting to this mechanism at the end of the first semester of organic chemistry, and obviously it affected the rest of my life because here I am talking about it for like the 14th year. It's Groundhog Day, my life, over and over again. But hey, I like this stuff. Here we go. Here's our alkyne. There's a pi bond represented, as two p orbitals, each with one electron, but we know the reality is somewhat more complex. Here's our sodium. It gives up an electron to one of these p orbitals. We get an alkyne radical anion. Okay, that deprotonates one of our molecules of liquid ammonia. We get sodium amide, and now we get an alkenyl radical, which is ripe to be plugged with one more electron, and that's what another sodium atom comes up and does. It plugs it with one more electron. We get an trans alkenyl anion, right? It sort of rearranges to put the most sterically hindered groups trans with respect to each other to avoid steric repulsion, and then it plucks off a hydrogen atom from ammonia, or ultimately water if you quench your reaction with water later. Although I guess the pKa of an alkene 44, that's going to be greater than the pKa of ammonia, about 35. So yeah, this would work. So there we go, a trans alkene, wonderful, and sodium amide. That would be what, 10 to the 9th? Yes, equilibrium constant. That's nice. All right, oxidation in a few minutes. Here we go. Oxidation. Oh, there's a favorite molecule of mine. That's, what is this? 1-ethynyl cyclohexanol. That's a beautiful little crystalline molecule. What can we do with it? Well, if we treat it with sulfuric acid and a little mercuric sulfate and water, wow, we oxidize that alkyne, right? It goes from an alkyne to what? A ketone, a methyl ketone, in fact. Neat. What's another way to oxidize our alkynes? Here we've got one octine. Here we have dicyclohexylborane. We do a hydroboration, right? And of course our boron ends up getting stuck to the least substituted carbon. And then we do an oxidation with hydrogen peroxide and sodium hydroxide, and we get something called an enol. Why do we call this an enol? Well, it's a mixture of an alkene and an alcohol. We don't normally see these things in nature except in things like curcumin, which is, a large component of turmeric, which stains our rice orange in our curry dishes. And we've all eaten, enols before, if we've had curry. Curcumin's supposed to be good for us. Anyways, most enol don't like to exist. They'd rather prefer the carbonyl form, so they do something called tautomerism, where they change to that carbonyl form. In this case, our enol becomes an aldehyde. Some enols become ketones. This is a big subject for the second semester of organic chemistry, but here's a little, preview, right, of how exciting the second semester of organic chemistry is going to go. How does tautomerism work in this case? Here we're in basic conditions, so sodium hydroxide protonates our enol, and then we'll drop a lone pair and snag a proton from water. This is called an enolate. Once we've snagged the proton from water, wow, we've converted to the aldehyde. That was easy, right? A few steps. How could the second semester be difficult? I don't know. All right, well, we're almost done within 10 minutes. Amazing, absolutely amazing. Alkynes in nature. This is ichthyotheriol. The natives of the lower Amazon basin collect this chemical from poison dart frogs by rubbing little arrowheads on their backs very carefully. If you slip and you cut yourself, yeah, you're going to be paralyzed, convulse, and probably die, because yeah, this stuff is perfect to sort of insert itself in the exact, sorts of pores that your cells need to conduct electrical nerve signals, right? And yeah, your heart stops beating, all sorts of bad stuff happens because yeah, that pump is just blocked by this, long alkyne tube. Oh well, tough for you. Don't play with poison dart frogs. That's always a wise mantra. All right, we're at 10 minutes. I don't know how we did it, but that's all in the notes for the first semester.